Part 8 of exercises acid-base, titration of polyprotic acid or base. Exercise 10, to phosphoric acid solution HCpO4, we add sodium hydroxide to reach the pH 9.5. Determine the concentrations of the phosphoric species present in the solution. We know when OH- is added to HCpO4, which is a triacid, we will have 3 consecutive reactions, and the predominance domain depends on the amount of OH- added, so it depends on the pH of the solution. The diagram of predominance species according to the pH, we know if we have a pH less than 4.7, which is the pH of ampholyte, H2PO4-, the couple present is HCpO4, H2PO4-, and the pH is determined by Henderson equation applied on couple 1. And from the ampholyte H2PO4- to the ampholyte HPO4-, we have the couple H2PO4- and HPO4-, and also we apply Henderson on couple 2, and for pH greater than 9.75 we have couple 3 and Henderson equation applied on couple 3. So at pH 9.5, so we are in this area, the predominant species are H2PO4- and HPO4-. That does not mean that other species containing phosphorus are not present. When we add OH- to HCpO4, we have all the species HCpO4, H2PO4-, HPO4-, and PO4-, but the predominant forms are H2PO4- and HPO4-. So at pH equal 9.5, pH equal minus log HCO plus in the solution, so HCO plus in the solution equal 10 minus 9.5. OH minus times HCO plus equal Kw, so OH minus equal Kw divided by HCO plus equal 10 minus 4.5. So we calculated the concentration of HCO plus and OH minus. The question is to calculate the concentration of all phosphorus species. The phosphorus species present in solution are HCpO4, H2PO4-, HPO4-, and PO4-. The law of mass conservation states that the number of moles of all forms of phosphorus species is equal to the initial number of mole of H3PO4, which is the main source of the phosphorus species in solution. So N0 HCpO4, the initial number of mole of HCpO4, is equal to the number of mole of HCpO4 in the solution plus that of H2PO4-, HPO4-, and PO4-. Since the total volume is constant, we divide by V total and we transform the number of mole to the concentration, so the initial concentration of phosphoric acid is equal to the concentration of all phosphorus forms equal 0.1. But we know that at pH 9.5, the predominant species are H2PO4- and HPO4-. So we can neglect HCpO4 with respect to H2PO4- and HPO4-, the same for PO4-. So finally, we have H2PO4 minus in the solution plus HPO4 2 minus in the solution is equal to 0.1. This is the first equation that relates the concentration of these two species in the final solution. So we have to think about another equation that relate this species, and for example, if we use the expression Ka2 equal H3O plus in the solution, which is 10 minus 9.5 times HPO4 2 minus divided by H2PO4 minus equal 10 minus 7.2. So we will have another equation that relate these two species. Therefore, we will have two equations to two unknown, and we calculate the concentration of these two species. So HCO plus equal 10 minus 9.5, equation 1, H2PO4 minus plus HPO4 2 minus equal 0.1, and equation 2 is the relation of Ka2, two equations of two unknown. We calculate the concentrations of H2PO4 minus and HPO4 2 minus. So till now, we calculated the concentration of HCO plus, OH minus, H2PO4 minus, and HPO4 2 minus in the solution. We have two other phosphorus forms, which are H3PO4 and PO4 3 minus. Using the expression of Ka1, we know HCO plus, we know H2PO4 minus calculated initially. So we calculated H3PO4, which is equal 2.5 10 minus 11. By using the expression of Ka3, we calculated PO4 3 minus equal 1.5 10 minus 4 molar. If we compare the concentrations obtained, as we said, H2PO4 minus and HPO4 2 minus will be predominant. H3PO4 is practically zero since the pH 9.5 is too far from the domain of predominance of H3PO4, and PO4 3 minus is in acceptable value since the value 9.5 is near the domain of predominance of PO4 3 minus. Exercise 11. Given the pKa values of polyacid HCpO4, which of the following statement are or is correct? pKa2 is associated to the couple HCpO4 PO4 3 minus. This is false. First, we don't have a couple HCpO4 PO4 3 minus. And second, pKa2 is associated with the couple H2PO4 minus HPO4 2 minus. pKa1 is associated to HCpO4 H2PO4 minus. This is true. At pH 1, PO4 3 minus is predominant. At pH 8, HPO4 2 minus predominant. At pH 10, PO4 3 minus is predominant. In this type of statements, we have to write the domain of predominance according to the pH. And we have this ladder diagram or domain of predominance explained previously. So at pH 1, PO4 3 minus is predominant. This is false. H3PO4 is predominant. D at pH 8, HPO4 2 minus is predominant at pH 8 in this area. This is true. At pH 10, PO4 3 minus is predominant at pH 10. This is false. At pH 10, HPO4 2 minus is predominant. So the correct answers are B and D. Determine the volume of sodium hydroxide that should be added to 30 ml of phosphoric acid in order to prepare a buffer solution of pH equal 7.5. As mentioned in the previous exercise, the addition of OH- to H3PO4 will transform it to other phosphorus species. So in this type of exercise, we have to write the ladder diagram or the domain of predominance of species according to pH, where we have 3 couples and 3 Henderson equation. The pH of the buffer solution is 7.5. So in this area, OH- added will transform H3PO4 completely to H2PO4-, then OH- added will react with a part of H2PO4- to transform it to HPO4-. The initial number of mole of phosphoric acid is 3 millimole, that of OH- 0.5 V. So we write the two reactions taking place. First, H3PO4 react with OH- completely, so H3PO4 is limiting. We have 3 millimoles, 0.5 V, 0. At T equal infinity, we have traces of H3PO4. We have 0.5 V minus 3 millimoles of OH- in excess, and we have H2PO4- 3 millimole. Now the excess of OH- will react with H2PO4-, so we have the other reaction in the second domain. H2PO4- plus OH- give HPO4-, and H2O. Initially, we have 3 millimole, OH- 0.5 V minus 3, 0. In this reaction, OH- should be limiting, since we have the couple H2PO4-, HPO4-. So at T equal infinity, we have traces of OH-, and we have 3 minus 0.5 V minus 3 remained of H2PO4-, and 0.5 V minus 3 formed of HPO4-. So in the new solution at pH equals 7.5, the predominant species are H2PO4- and HPO4-. So we apply Henderson equation on this couple. pH equal pKa2 plus log concentration of the base HPO4- divided by the acid H2PO4-, and since V is constant, so is pKa2 plus log number of moles divided by the number of moles implies the pH of the buffer is 7.5, pKa2 7.2 plus log, the base is 0.5 V minus 3 divided by the acid, which is H2PO4- is 6 minus 0.5, so we can calculate the volume is equal 10 milliliter. So, as a conclusion, if 10 milliliter of the base NaOH were added to H3PO4, it will transform it to a buffer solution of pH equal 7.5. Exercise 51, we add to HA sodium hydroxide solution. The first equivalence point is at 40 milliliter, the second is at 80 milliliter. Part A, write the corresponding reactions and give the expressions of pH at the half equivalence and at the equivalence. In this type of exercise, the best method is to make a summary of the data. The number of mole of A equals CaVA, so the volume of the acid initially taken is 40 ml. At the first equivalence point, VE1 equal 40 milliliters and pHE1 equal 5.85. At the volume 60 milliliter, the pH given is 8.08. And at the second equivalence point, VE2 equal 80 ml. The reaction taking place when OH minus is added to HA, we have two consecutive reactions. H2A plus OH minus give HA minus plus H2O. HA minus continue the reaction with the OH minus added to produce A2 minus and H2O. To note that these two reactions are complete. According to the titration curve, we have specific points V equals 0, VE1 divided by 2, the first half equivalence point, VE1 the equivalence point, 3 VE1 divided by 2 is the second half equivalence point, and VE2 equal 2 VE1 is the second equivalence point. So at the first equivalence point at VE1 divided by 2, the pH is equal pKa1 of the couple H2A, HA minus. At the first equivalence point, HA minus is ampholyte, so the pH equal half pKa1 plus pKa2. At the second equivalence point at 3 VE1 divided by 2, the pH is equal to pKa of the second couple, HA minus, A2 minus, so pH equal pKa2. At the second equivalence point, VE2 equal 2 VE1, VE2 equal 2 VE1, the pH of the solution is equal 7 plus half pKa2 plus half log A2 minus in the solution at VE2, or POH equal half pKb1 plus P concentration of A2 minus at the second equivalence point. Determine the values of the acidity constant Ka1 and Ka2. As we said, Ka1 and Ka2 are deduced from the half equivalence points. At VB equals 60 milliliters, the pH given is equal 8.08. pKa1 and pKa2 are deduced from the half equivalence point VE1 divided by 2 and 3 VE1 divided by 2. So if VE1 is equal 40 ml, this is given in the data, 3 VE1 divided by 2 equals 3 times 40 divided by 2 equals 60 ml. So the volume of the base 60 ml is equivalent to 3 VE1 divided by 2. So the pH 8.08 is equal to pKa2 and Ka2 equal 10 minus 8.08. From the pH ampholyte, which is at VE1, we have pH equal pKa2 plus pKa1 divided by 2 equal 5.85. We calculated previously Ka2, so we can deduce pKa1 equal 3.62 and Ka1 equal 10 minus 3.62. Part C, calculate the pH at the equivalence point. We know at the second equivalence point, H2A completely transformed to A2 minus. So the number of moles of A2 minus at the second equivalence point is equal to the initial number of mole of H2A. And the pH will be determined by A2 minus, which is a dibase. What is the concentration of A2 minus at the second equivalence point? The concentration of A2 minus at VE2 is equal to the number of moles of A2 minus at VE2 divided by V total. And the number of moles of A2 minus at VE2 is equal to the initial number of mole of H2A present. So equal 4 10 minus 3. Divided by V total. V total is equal to the V acid initial taken in the titration plus the volume of the base added. So is equal to VA initial plus VE2, which is equal to 2VE1. So the concentration of the base at VE2 is equal 410 minus 3 divided by 40 plus 80 times 10 minus 3, since the volume should be in liter. So the concentration of A2 minus is equal to 0.033 molar. The pH of the solution is the pH of weak dye base. The pH of weak dye base is deduced if we compare the first basicity of the base and the second basicity. So we have to compare KB1 and KB2. KB1 and KB2 are not given. In this problem, we deduce Ka1 and Ka2. We know that Ka and Kb are related. pKa plus pKb of the same couple equal pKw. In the dye base, we have to pay attention that to pKa1 corresponds pKb2. To the first acidity correspond the second basicity. So pKa1 plus pKb2 equal pKw. And pKa2 of the couple is related to pKb1 of the same couple. So pKa2 plus pKb1 equal pKw. And we deduced by this way Kb1 and Kb2. Now we have to compare the first basicity pKb1 to the second basicity pKb2. And if Kb1 is greater or equal 100 Kb2, that means the second basicity could be neglected. And this is our case. This relation is valid in this problem. So A2 minus can be considered as a weak monobase. That means we consider only the first basicity and we neglect the second. So the problem passes to the pH of weak monobase. To calculate the pH, we have to compare the concentration of the base with respect to Kb1. C0 greater or equal 100 Kb1. If this relation is valid, and this is our case, so the pH can be deduced directly equal half pKw plus half pKa2 plus half log concentration of the base, or we use pOH equal half pKb1 plus P concentration of the base. We can use pOH, then deduce pH, or we can use directly the pH formula. But pay attention, in the expression of pOH appears pKb1, in the expression of pH appears pKa2. And in our course, we proved these two relations. So pH equals 7 plus half 8.08 plus half log the concentration of the base found previously at VE2 equals 0.33. So the pH equal 10.43. Exercise 52. The titration of 10 milliliter of H2CO3 is done by NaOH. Calculate the pH for the solution after the following additions of the base. to note that X is the degree of progression of titration, which is equal to the volume added divided by the volume at equivalence. So in this type of exercise, we have the titration of diacid by a base. So we will obtain by theory two jumps. The first is the titration of the first acidity of H2CO3. The second is the titration of the second acidity. Before starting the calculation, in this type of exercises, we calculated V equivalence. So the volume at equivalence, the number of mole of A equal the number of mole of B, implies CAVA equal CBVB E1. So the volume at the first equivalence is 5 milliliter. On the draft, we can draw the curve of the titration. So we have two jumps. The first for the transformation of H2A to HA minus, and in the second part of the curve, we transform HA minus to A2 minus. So the volume at equivalence is 5 milliliter. We calculated the volume at the characteristic point at the starting V equals 0, VE2 divided by 2, 5 divided by 2, 2.5 ml, and we continue for the other volumes. So in this type of exercise, we have to make a table where we have the volume of the base, what is the domain, the species present, and the formula used. If we know, for example, what is the volume added, we can apply directly the formula. For example, before addition of the base V equals 0, so the domain is before addition of base, the species predominant or present is H2CO3, which is a diacid. We have to see if it behaves as monoacid, then to study the domain of validity to see if we apply the formula pH equal half pKa 1 minus half log C. At volume of base 2.5, this is the first half equivalence point. So the species present are H2CO3 and HCO3 minus in equal concentrations. So the pH is equal to the pKa of the couple involved, which is pKa 1. At volume 3.5, so we are after equivalence. The species present are H2CO3 and HCO3 minus, but H2CO3 is greater than HCO3 minus since we are after the half equivalence point. And the formula is the formula of Henderson, pH equal pKa plus log base over acid. At volume equal 5, this is the equivalence point. The species present are HCO3 minus and folate, so the pH is equal half pKa1 plus pKa2. At 6.5, so this is the point after the first equivalence. So we pass to the second couple, HCO3 minus CO3 minus, and the formula applied is Henderson, pH equal pKa2 plus log base CO3 minus divided by the acid HCO3 minus. At 3VE1 divided by 2, this is the second half equivalence point, and at the second second half equivalence point, the pH is equal to pKa of the second couple, so pH equal pKa2, and the species present are HCO3 minus and CO3 minus. At 8.5, so we are after the second half equivalence point. The species present are HCO3 minus and CO3 minus, and CO3 minus is greater than HCO3 minus since we pass the second half equivalence point, and the pH is the pH of Henderson, pH equal pKa2 plus log base over acid. At V equal 10 ml, this is the second equivalence point. So all H2A has been transformed to A2-, and the species present are CO3-, and the pH is the pH of dibase. We have to look if CO3-, behaves as monobase, then to compare CB to KB1. If it's valid, we apply the relation POH equal half PKB1 minus half log C prime. And to note that the concentration of CO3-, at the second equivalence point is equal to the number of moles of H2A initial divided by V total, which is equal to V0 of the acid taken plus the volume added, which is VE2. At 13.5, so we are after the second equivalence point, we have CO3-, that is formed at VE2 plus the OH- in excess, and since OH- is a strong acid, it will determine the pH, then POH equal minus log OH- in excess, then we deduce the pH. So we have to look for the volume and the formula applied. We start the calculations. First, at VB equals 0, so before addition of the base, we have H2CO3. Ka1 is greater or equal 100 times Ka2. H2CO3 behave as monoacid. C0 is greater than 100 Ka1. This is valid. So we apply directly the relation pH equal half pKa1 minus half log C, and the pH equal 4.31. For the volume 2.5, this is at the first half equivalence point. So the pH equal pKa1 equal 6.32. If we want to prove, for example, this value of pH, we write the reaction between H2CO3 and OH-, and OH- is limiting. We have at T equal infinity, we have H2CO3 and HCO3-. We apply Henderson formula and we find the same value. At V base added equals 3.5 milliliter. This is after VE1 divided by 2 and before the equivalence point. So the predominant species are HCO3- and H2CO3. We apply Henderson on this relation, but we have to write the reaction and to find the concentration of H2CO3 and HCO3- at equilibrium. So initially, we have 0.05 of H2CO3. We add 0.035 of the base, HCO3- 0. The reaction proceeds till T equal infinity. OH- is limiting, so we'll have traces, and the remained H2CO3 is 0.065. HCO3- is equal to 0.035 millimole formed. So we have the acid and its conjugate base. They behave as a weak acid and weak base behaviors. So the concentrations at the new equilibrium are practically obtained in the first equilibrium. Therefore, we apply Henderson pH equal pKa of the couple involved plus log concentration base over acid, and the pH equal 6.688. At V equal 5 milliliter, this is the first equivalence point. As we know, at the first equivalence point, all H2CO3 has been transformed to HCO3-, and this is ampholyte. We apply the pH of ampholyte equal half pKa1 plus pKa2, and the pH equal 8.32, which is basic. At VB equals 6.5, so we are after the first equivalence point. The number of mole of base added equal concentration times the volume added, and the initial number of mole of acid equals 0.05. So we write the reactions. Here we have two reactions. First, the OH minus added will transform H2CO3 to HCO3 minus. Then the OH minus remained will transform a part of HCO3 minus to CO3 2 minus. So at t equals 0 in the first, we have 0.05, 0.065. H2CO3 is limiting since it's completely transformed. We have 0.015 OH minus and 0.05 of HCO3 minus. Now the reaction starts between HCO3 minus at equilibrium and OH minus at equilibrium, 0.05, 0.015, and OH minus is limiting, so we will have a couple HCO3 minus, CO3 2 minus, and we apply Henderson on the concentrations or the number of moles obtained at equilibrium. So pH equal pKa2 plus log concentration base CO3 2 minus divided by the acid. HCO3 minus equal pKa2 plus log 0.015 divided by 0.035 equal 9.95. To note that instead of working on the two separate reactions, we can work directly on the global. H2CO3 plus 2OH minus give CO3 2 minus plus 2H2O, and we will obtain the same answer. In part F, the VB equals 7.5 milliliter. This is the second half equivalence point, and at the second half equivalence point, the pH equal pKa of the couple involved. So pH equal pKa 2 equal 10.32. We can prove this relation by writing the reaction between H2CO3 and OH minus till T equal infinity. Then HCO3 minus to CO3 2 minus. The species predominant are HCO3 minus and CO3 2 minus, and we apply Henderson, we obtain the same answer. But it's not necessary to do this calculation. In part G, for the volume of base equal 8.5 milliliter, we repeat the same work as part E. Calculate the pH for the volume of the base added equal 10 milliliter. This is the second equivalence point. At the second equivalence point, all HCO3 has been transformed to CO3 2 minus. The number of mole of CO3 2 minus is equal to the initial number of mole of H2CO3 equal 0.05, and the concentration of CO3 2 minus is equal to the number of mole divided by V total, and V total is equal to 20 ml, so the concentration equals 0.0025 molar. The pH is determined by CO3 2 minus. We compare Kb1 and Kb2. We find that Kb1 of the couple is greater or equal 100 times Kb2, so CO3 2 minus behaves as weak monobase. We pass to the domain of validity. The concentration of CO3 2 minus is not greater or equal 100 times Kb1. So the formula pOH equal half pKb1 plus Pc prime could not be applied in this case. We have to apply the second degree equation, x2 plus Kb1 x minus C0 Kb1 equal 0, and we find x equals 6.25, 8, 10 minus 4 molar. So x is the concentration of OH minus in the solution, so we can calculate pOH. Then pOH equal minus log x. Then pH plus pOH equal pKw, and we find pH equal 10.796. At Vb equal 13.5 ml, we are after the second equivalence point. So after equivalence point VE2, we have base in excess, and we have the CO3 minus formed at VE2. So this volume of the base added 13.5 milliliter. A part of this volume transformed H2CO3 to CO3 minus, and the other part remains in excess. So the corresponding reaction is H2CO3 plus 2OH minus gives CO3 minus plus H2O. Initially, we have C of the base CbVb equals 0.135, and of H2CO3 initial 0.05. So this reaction proceeds till T equal infinity, and we have epsilon of H2CO3 and OH minus is in excess, which is equal 0.135 minus the part of OH minus reacted, which is 0.1. Number of mole of H2CO3 reacted divided by 1 is equal to the number of mole of OH minus reacted divided by 2. So at the end, we will have 0.035 millimole of OH minus in excess, and we have formation of 0.05 millimole of CO3 minus. So after VE2, we have two bases, one which is weak and the second is strong, and the strong will determine the pH of the solution. The concentration of OH minus in excess is equal to the number of mole of OH minus in excess, 0.035 divided by V total. V total is equal to the V0 of the acid plus the volume added, which is 13.5 milliliter. So the concentration of OH minus in excess equal 1.489 10 minus 3 molar. We apply pOH equal minus log OH minus, pOH equal minus log OH minus in excess, pOH equal minus log 1489 10 minus 3. So we find pOH, then pH plus pOH equal pKw, and the pH equal 11.17. Exercise 53, we titrate 10 ml of sodium carbonate Na2CO3, CO3 minus is a dye base, by HCl 0.1 mole per liter. In the previous exercise, we titrate dye acid by OH minus, the dye acid was H2CO3. In this exercise, we titrate a dye base by HCO plus. So this is the inverse curve. Write the hydrolysis reactions of the dye base and indicate the basicity constant Kb1 and Kb2. The reactions are CO3 minus in water, the hydrolysis, so we use water, give HCO3 minus plus OH minus, then HCO3 minus dissociate in water to give H2CO3 and OH minus. The first reaction has a value K reaction equal Kb1, this is the first basicity, and the second reaction has a value Kb2. How to deduce Kb1 and Kb2 given pKa1 and pKa2? To pKa1 corresponds pKb2, and to pKa2 the corresponding is pKb1. So pKa2 plus pKb1 equal pKw, and pKa1 plus pKb2 equal pKw. So we calculate Kb1 and Kb2. Part B, calculate the pH of the dye base alone in the medium. So this is before the addition of HCl. Before the addition of HCl, we have a dye base CO3 minus and this dibase behave as monobase since Kb1 is greater or equal 100 Kb2. And second, in the domain of validity, the concentration of the base is greater or equal 100 times Kb1. So we apply directly the relation POH equal half pKb1 minus half log C, and the POH equal 2.35. Then pH plus POH equal pKw, so the pH equal 11.65. Another method is to apply directly the pH. pH equals 7. Pay attention, plus half pKa2 plus half log C, because pKa2 corresponds to pKb1. So the pH is equal 11.65. Let's see, according to the degree of progression of titration, calculate the pH of the medium for x equal 1.2 and x equal 2. It's better to draw on the draft the titration curve of CO3 2 minus by HCl. So we have two jumps that corresponds to 2 basicity. Before addition, we have CO3 2 minus. At the first equivalence point, we have HCO3 minus. At the second, we have H2CO3. And we have to put the corresponding specific points. So at x equals 0, we apply the relation POH equal half pKb1 plus pC0, or pH equals 7 plus half pKa2 plus half log C0. At the first equivalence point, which is x equals 0.5, so the pH equal pKa2. At the first equivalence point, so x equal 1, this is ampholyte, pH equal half pKa1 plus pKa2. At the second equivalence, at the second half equivalence point, which is 3VE1 divided by 2, the pH is equal pKa1. This is the couple 1. And at the second equivalence point, we have a diacid, so we apply the relation pH equal half pKa1 minus half log C prime. After the second equivalence, for x greater than 2, we have excess of the acid, so pH equal minus log HCO plus in excess. This graph make easier the reading of the degree of progression of titration and what should be the formula used. So at the first equivalence point, the number of mole of base equal number of mole of acid, so the V equivalence is equal 10 ml. VE1 is equal 10 ml. Now we have to calculate the pH of the solution for x equal 1.2. For x equal 1.2, so we are after the first equivalence point. X equal 1.2, so VA divided by VE1 equal 1.2, so the volume of the acid equal 1.2 times the V equivalent, so V acid equal 12 ml. So X equal 1.2 is similar to a volume of the acid added 12 ml. So the 12 ml added transforms CO3 to minus first to HCO3 minus, then a part of HCO3 minus to H2CO3. So we have two reactions. We work on the two separate reaction, or we can work on the global reaction. So CO3 2 minus plus HCO plus give HCO3 minus plus H2O. At T equals 0, 1, 1.2, 0. CO3 2 minus has been completely transformed, so is limiting, and we have 0.0 millimole of HCO plus in excess, and HCO3 minus formed 1 millimole. Then another reaction starts between HCO3 minus and HCO plus. So at T equals 0, we have 1, HCO plus 0.2, we have to correct, this is HCO plus 0.2, H2CO3 0, HCO plus is therefore limiting, and we will have the couple HCO3 minus H2CO3 0.8, 0.2. So we apply Henderson formula, pH equal pKa involved. The pKa involved in for the volume 12 ml is the couple H2CO3, HCO3 minus, so pKa1 plus log concentration of the base divided by the acid, and the pH is therefore equal 6.9. Now we calculate the pH for x equal 2. So we are at the second equivalence point at volume equal 20 ml. The degree of progression of titration x equal 2 is equivalent to a volume of the acid added 20 ml. At this point, the second equivalence point, all CO3 minus has been transformed completely to H2CO3. So we have a diacid. The number of moles of H2CO3 is equal to the number of mole of CO3 minus initial, and the concentration is the number of mole divided by V total, and V total is equal to the volume of CO3 minus initial 10 ml plus the volume of HCl added 20 ml, so the total volume is 30 milliliters. The concentration of H2CO3 is equal to 0.0334 molar. So the pH will be the pH of the diacid H2CO3. We compare Ka1 and Ka2. We find Ka1 greater or equal 100 times Ka2. So H2CO3 is considered as weak mono acid. Then we pass to the domain of validity, and we prove C0 is greater or equal 100 times Ka1. So we apply directly the relation pH equal half pKa involved, which is pKa1, minus half log C, and the concentration of H2CO3 was calculated. So the pH is equal to 3.88. Part C, calculate the pH of the medium for volumes 6 milliliters and 10 milliliters. So for the volume 6 milliliter, the number of moles of acid added is equal CAV. A equals 0.6 millimole. And we are before equivalence. The V equivalence is 10 ml. So 6 ml is before equivalence. So all HCO plus added will completely react. At T equals 0, the CO3 minus initial 1, HCO plus added 0.6. At T equal infinity, we have traces of HCO plus, and we will have 0.4 millimole of CO3 minus and 0.6 millimole of HCO3 minus. So we apply Henderson equation, pH equal pKa of the couple involved, which is pKa2 plus log concentration of the base divided by the acid, and therefore the pH equal 10.12. At volume equal 10 ml corresponds to x equal 1. This is the first equivalence point. So at the first equivalence point, we transform all H2CO3 to HCO3 minus, which is an ampholyte. So the pH of the solution will be the pH of the amphoteric solution, pH equal half pKa1 plus pKa2, and the pH equal 8.3, which is basic. The last exercise in the part 8, exercise 55, consider the titration curve of unknown solution H2A by NaOH. This problem is the same as the titration of H2CO3 by OH minus solved in the previous exercises. So this is the titration curve. we have two jumps. The first corresponds to the transformation of H2A to HA minus. The second, the transformation of HA minus to A2 minus. And we have the characteristic points V equals 0, the half equivalent, first equivalence, the first equivalence point, the second half equivalence point, and the second equivalence point. So according to the curve, VE1 equal 20 ml, VE2 equal 40, and the first half equivalence point at 10 milliliter, the second half equivalence point at 30. Question 1, what is the concentration of the acid in the initial solution? At equivalence, the number of moles of the acid equal number of mole of base, so CaVA equals CB VE, and the volume at equivalence is 20. The concentration of the base is 0.1 divided by the initial volume of the acid 20 ml. So the concentration of the acid is equal to 0.08 molar. Part B, determine Ka1 and Ka2. Ka1 and Ka2 are determined respectively at the first half equivalence point and the second half equivalence point. So at the first equivalence point, pH equal pKa1 equal 2.5, and we calculated Ka1. At the second equivalence point, pH equal, at the second half equivalence point, pH equal approximately 6.7, so we calculated Ka2. Part C, a solution of NaH in water is acidic or basic. We know that HA minus, when we dissolve NaH in water, we obtain Na plus spectator, and HA minus, which is ampholyte. So the pH will be the pH of ampholyte, half pKa1 plus pKa2, 2.5 plus 6.7 divided by 2 equal 4.6. This is the value 4.6. So the solution is acidic.